Today we're starting chapter 10. Chapter 10 deals with all radicals. So today we're going to be simplifying radicals, and then we'll be adding, subtracting, multiplying, and dividing radicals, solving equations with radicals, and graphing radical functions this chapter. So this is lesson 10.1. Simplifying radicals. First, we're going to look at the multiplication property of square roots. And the multiplication property of square roots is basically just saying that if you have the square root of AB, that can be equal to the square root of A times the square root of B. And it goes the other way also. If you have the square root of A times the square root of B, you can multiply those together and you'll have something under one square root together. So you can split stuff up or multiply it together as long as it's all under a square root. When you're looking at this, A always has to be greater than or equal to 0, and B always has to be greater than or equal to 0, and that's because we can't have the negative numbers underneath the square root to have real numbers. So an example of this would be something like the square root of 2a, and you can split that up and it can be the square root of 2 times the square root of a. Or if you had the square root of 2 times the square root of a, you could multiply that together and have it under the square root together. When you learned how to do the quadratic formula, we used calculators in the last chapter because I told you we're going to learn how to simplify radicals when we got to chapter 10. So when you were looking at the quadratic formula and you had your discriminant underneath your square root, you always had to use a calculator if it wasn't a perfect square. And what we're going to start doing with those now is you're actually going to simplify those radicals without using a calculator by doing what you're going to learn right now. So this is two different ways to do this. The first way we're going to look at it is by removing perfect square factors. And you want to start looking for the patterns of when it's easier to do this or the other one that you're going to learn. So example 1. Simplify the square root of 192. So this would be like if we were talking about the quadratic formula, you'd have plus or minus square root of 192. And then you would simplify this piece and leave the negative b plus or minus and leave the over 2a part. So what you're going to look for is a perfect square that goes into this number. And sometimes you'll see them, they're pretty easy. Other times you might have to look for a minute. But in this case, I know that 64 goes into 192 3 times. So I'm going to break it down into two pieces. I have the square root of 64 times the square root of 3. If I was to multiply those together, I'd have the square root of 192. Now I can break it down further. I can take the square root of 64. The square root of 64 is 8, and the square root of 3 is just square root 3. And you can treat these radicals like a variable. So 8 square root 3 just means 8 times the square root of 3, just like if it was an 8x and you'd have 8 times x. And that's your answer. You always want to check in the radical and make sure that this doesn't break down further. And 3 doesn't break down further, so I'm done. Okay, so let's write down over here what you're going to do. So you find a perfect square factor. And then you break the radicand. into two parts, sometimes more depending on how many times you end up breaking it down. And then you take the square root of the perfect square factor, and when you take the square root, you actually get to drop the square root sign. Only time you're ever going to drop the square root is when you're actually taking a square root. So make sure you leave square roots with things that don't have a perfect square. And then you leave the square root around everything else. And then again, you always want to check to make sure that it doesn't break down further. Okay, we're going to try a few more of those. This is example 1b. Simplify the square root of 50. So you want to look at 50 and you want to make sure you're looking for perfect square factors. So a lot of you might see 5 times 10, but you don't want to use 5 times 10 in this case because you're looking for a perfect square factor. So you have to look for something that's a perfect square. Perfect square is 25, so the square root of 25 times the square root of 2 gives you 50. And then you break it down further, the square root of 25 is 5, and the square root of 2 just comes down as 5 root 2. So the square root of 50 simplified is 5 times the square root of 2. And the main reason that you're simplifying these is because now you have a better picture for what number this really is, versus up here is the square root of 50. It's just simplified. It's easier to think about it in terms of something we understand. Okay, negative 5 times the square root of 300. So in this case, you already have an integer in front multiplying to the square root of 300. So you're just going to bring that integer down with everything as you break down the square root of 300. And it will just combine with any other integers and multiply at the end. So bring down negative 5. And now you're looking for a perfect square factor that goes into 300. And that's 100 times the square root of 3. So you have negative 5 times the square root of 100 times the square root of 3. Now you're going to break down the square root of 100, so you have negative 5 times 10 times the square root of 3. And now you can go ahead and multiply your integers. So a negative 5 times 10 is a negative 50. And then the square root of 3 comes down, and that's your answer. Okay, there's another way that you can look for these to break down. And either way works, so you just have to be aware of it. So the other thing that you need to look for is every time you see two matching radicals, because this will happen every once in a while and not be a perfect square factor, but you can see a perfect square factor. They end up canceling the radical. So I'm going to show you an example of that right here. If we took the example 1b, the square root of 50, if you were to take the square root of 50 and you didn't choose 25 as your perfect square factor, even though you always want to look for a perfect square factor, just in case sometimes you're going to see this and you want to be aware of it because it makes it a lot easier. So let's just say someone chose to break this down as the square root of 5 times the square root of 10. So at this point, nothing breaks down into a perfect square. But then they notice that the square root of 10 breaks down into the square root of 5 times the square root of 2. So this square root of 5 comes down, and then they have another square root of 5, and then square root of 2. This is the matching radicals that I was just talking about. And if you think about that, these together make the square root of 25, which is 5. So the radicand just cancels and you bring a 5 down. Or if you're going to forget that, just multiply them together. You get square root of 25, take the square root of 25, and you have 5. And then the square root of 2 still comes down. So always be aware of those matching radicands also. Okay, there's another thing that we're going to look at. This is when we have variables. And you've already been doing this a little bit when we've been talking about the square root of x squared. So this shouldn't be difficult for you. It's just talking about when we have something other than x squared all the time. Every time you have an even exponent, you just divide it in half. And that's your square root. So you'll just drop your square root, your radicand after that. So here's an example of that. Example 2 is simplify the square root of 27n squared. So first you need to break down 27. So look for a perfect square factor. And the perfect square factor was 9. So you have the square root of 9 times the square root of 3. And then your n squared is its own piece here. And because it's even, when you go to simplify that, you're just going to divide it in half. So that's what you've been doing when you've been finding the square roots of your squareds. Half of 2 is 1, and so an n would drop down. So now you have the square root of 3, and you have the square root of 9, which is 3, and then the square root of n squared, which is n left over. And your final answer, you want to have everything outside of the square root at the front, and then the radicand at the back, just like you would a variable. So it ends up being 3n times the square root of 3. Okay, we're going to try another one of those. Square root of 45, a to the 5th. So this time our exponent is odd. And if you think about it, every 2, we have 1 square root of every 2 that comes out of this radicand. So what's going to happen here is when you have an odd number, you're going to have 1 that doesn't partner up and cancel out. So whenever you see an odd exponent, you're going to have that one oddball that ends up left in the radicand at the end. And what you're going to do is split this up. You're going to pull the the odd one out, and then you'll have the even number left over. So you break down 45, and what goes into 45 that has a perfect square? It's the square root of 9 times the square root of 5. And then this a, because it's odd, I'm going to go ahead and take 1 away from it, so a to the 4th, and leave 1 by itself. Now this one is going to simplify. Half of 4 is 2, so an a squared is going to drop out of there. So I have the square root of 9, which is 3, square root of 5, which doesn't break down any further, square root of a to the 4th, which becomes an a squared by taking half of the exponent, and then a square root of a, which doesn't break down any further. And now I'm going to combine everything on the outside of the radican, and then multiply everything on the inside back together there. So I have 3 times a squared, which is 3a squared, times the square root of 5 times a, which is 5a. And that's the simplified radical. So when you have these odd ones, just remember, split it in 2. Okay, you're going to split it into 2, so 1 you're just going to have that oddball that was left over, and then the even amount would be left right there. And that's the one you can simplify. Negative a times the square root, 60 a to the 7th. So this negative a just comes down. You don't do anything with that. Now you're just going to look at 60. Think of a perfect square factor that goes into 60. And I found 4. So square root of 4 times the square root of 15 gives me 60. Now I see my variable, and my variable has an odd amount of exponents, so I need to go ahead and break that one apart too. I'm going to have the 1 that's left over, and I had 6 to make it even. So the 6 and the 1, total of 7 a's. And make sure you don't lose any number that was out in the front as you're breaking it down, so you always want to bring that down each time. So I have a negative a, square root of 4 breaks down into 2, so times 2. Square root of 15 doesn't break down into a perfect square. It has the factors 5 and 3, but there isn't a 5 or a 3 up here in the square root, so it doesn't matter. So I'm just going to leave it as the square root of 15. A to the 6th breaks down into a to the 3rd. And then the square root of a stays square root of a. Now I'm going to go through and combine everything that's on the outside of the radican. So I have 2 times a, I have 1a here and 3 here, so that is a to the 4th total, and I have the negative. So it's a negative 2, a to the 4th. So I got 2 times the negative is the negative 2, a to the 1st, a to the 3rd is a to the 4th. And then there's the square root of 15 and square root of a left, and so that comes over together as a square root of 15a. And then I always look and I make sure there's a perfect square factor left, and there isn't. Okay, we'll try another one of those. Square root of x squared y to the fifth. So we just have variables here. Again, you're just looking at each piece individually. So x squared is already even, so we can leave it as a square root of x squared. Y to the fifth is odd, so we need to break that down into two. We have a y to the fourth, and then we have the one that was left. Now we can break these down. The square root of x squared, half of 2 is 1, so we have an x. Square root of y to the fourth, half of 4 is 2, so we have a y squared, and then the square root of y left over. The next set of examples we're going to be looking at is multiplying two radicals. And this is similar to what we were just doing, because you're still going to need to simplify them. So you have a couple different ways that you can do it. I'm going to show you both ways with the first example. This is example 3. Simplify the square root of 8 times the square root of 12. So the first way you can do it is you just multiply the two radicals together. Keep them as a radical. So 12 times 8 is 96. And then you simplify 96. If you notice, square root of 8 didn't have a perfect square. Square root of 12 wasn't a perfect square. So I couldn't automatically just simplify one of those. So this time I'm multiplying the two together. And then I have to find a perfect square factor that goes into 96. You always want to try and find the largest perfect square factor. Some of you might have noticed that 4 goes into 96, but 4 isn't the largest. The largest is 16. So if I have the square root of 16 times the square root of 6, and now I break that down, the square root of 16 is 4, and square root 6. So sometimes this is difficult because in this case it was hard to figure out 16 was the largest perfect square factor. So the other way that you can do this to make it a little easier is break each of these down individually. So I have the square root of 8 times the square root of 12. And I'm just going to break down 8. So perfect square factor that goes into 8 is 4. 4 times 2. That's still the square root of 8 if I was to multiply it. And then I'm also going to break down 12. So a perfect square factor that goes into 12 is 4. 4 times 3. So now I have the square root of 4 times the square root of 2, which gives me the square root of 8, and the square root of 4 times the square root of 3, which gives me the square root of 12. And now you're going to look for perfect square factors or matching radicals. In this case, square root of 4 times square root of 4 is the square root of 16, and the square root of 16 is 4. Or you could break these down individually and have a 2 here and a 2 here, which also gives you 4 once you multiply them. But if these hadn't been perfect squares and they were matching, then you would just bring 1 4 down. Then I have a square root of 2 left and a square root of 3 left. So now I multiply the numbers on the outside of the radicand, which are 2 times 2. That's 4. And then I multiply what's inside, which is 2 times 3. And that's square root of 6. So same answer either way. So you can multiply the radicans together. Then simplify. Or simplify each individually and look for perfect square radicans or matching pairs. And remember with the matching pairs, it's something like this. If I had the square root of 3 times the square root of 3, then that just comes together and becomes a 3, because it's the square root of 9, which is 3. So you're only bringing one down and you're dropping the square root. And then just be really careful when you're dropping your radical signs, because you're only dropping them when you're taking the square root. Otherwise, you need to leave them. Okay, let's try another one. 3 times the square root of 2b times 4 times the square root of 10b. So again, either way works. You can break them down individually, or you can multiply what's in the radican together, multiply what's outside together, and then break it down. So we'll do it both ways again. So first we'll break them down individually. So we have 3 square root 2b times 4 square root 10b. So your 3 just comes down. Square root 2 comes down. Square root b comes down. These didn't break down at all. Times 4. 4 already was outside of the radican. And now you can break down 10 into 2 and 5. And then you still have this b. So now you want to go through and look for things on the outside of the radical already. So we have 3 and 4. So 3 times 4 is 12. Then you want to look for matching radicans, matching pairs right here that are going to become one of that number. There's a square root of 2 and there's a square root of 2. So that would be the square root of 4, which is 2. So 12 times 2. And then there's also a set of matching b's. So again, square root of b times square root of b is square root of b squared. So that's just 1b comes out. And then you have the square root of 5 left. Now you can multiply everything on the outside together. So 12 times 2 is 24b times the square root of 5. Okay, now let's try it the other way. So we would have had 3 square root 2b times 4 square root 10b. And you're just going to multiply everything on the inside together and everything on the outside together. So 3 times 4 is 12. And then 2b times 10b is going to be the square root of 20b squared. And now you want to look for a perfect square factor. So bring your 12 down. And the perfect square factor is 4 times 5. And this was even. So I can just bring it down one time. So now I have 12 times 2 times the square root of 5 times b. So that's everything simplified. 12 times 2 is 24 times b. So we have 24b square root 5, which is the same answer. Okay, now we're going to talk about dividing radicals. And you've already been doing a little bit of this in chapter 9 when you were simplifying radicals. But you've been simplifying ones that were perfect squares. So now you're going to be looking at perfect squares and radicals that aren't perfect squares. So when you're looking at the division, it's almost the same as multiplication. You can have the square root of some term being divided by another term, and you can actually split that and just look at the square root of the numerator and then the square root of the denominator. Or you can combine it and look at both together. So you're going to start to see the patterns of when it's easier to use one or the other. And again, a always has to be greater than or equal to 0, and b always has to be greater than or equal to 0. Because we can't have negatives with square roots. So an example of this would be something like, if I was given the square root of 16 over 25, I notice that this is a perfect square and that's a perfect square. So instead of dividing 16 by 25 and then trying to find the square root, it's going to be easier for me to look at it as just the numerator simplified and just the denominator. So if I take the square root of 16 individually, I get 4. And if I take the square root of 25 individually, I get 5. And so my answer would be 4/5. So let's look at some of those. This is example 5. We skipped example 4. We're going to go back to example 4. Square root of 11 over 49. What you're always going to be looking for is one of these a perfect square. And if it is, then you want to go ahead and split them into the top and the bottom, separate the numerator and the denominator. If they aren't a perfect square, then you can just simplify within the radical first. So because 49 is a perfect square, I'm going to go ahead and split this up into the square root of 11 over the square root of 49. And now I have the square root of 11 over, what is the square root of 49? 7. And then I look at the square root of 11 and I make sure it doesn't simplify at all. And there's no perfect square factor in the square root of an 11, so this is my final answer. So if we had the square root of 25 over b to the 4th, again I see a perfect square factor and another perfect square factor, so I want to go ahead and split it into just looking at the square root of the denominator and the numerator individually. So what is the square root of 25? It's 5. And what is the square root of b to the 4th? B squared. And that's your answer simplified. And then you'll get some that will have a little more involved with them. So for example, this one, we have square root 25p to the 3rd over q squared. So again, immediately I see a perfect square factor and I see a perfect square factor. I know this one isn't going to break down perfectly, but I know how to break that down from simplifying earlier. So you're just going to look at the top, square root of 25 times, and then again this was odd, so we want to take 1 away from it, so we have p squared, and then that oddball left over right there. And that's your numerator. And then over the square root of q squared. So now you're just going to break down the pieces that break down. So the square root of 25 is 5, square root of p squared is p, square root p left over, and the square root of q squared is q. And that's simplified. And I always check to make sure nothing simplifies within my fraction or my radical. So when you're simplifying fractions with radicals, if you see any perfect squares, split the numerator and denominator. To simplify individually. Always keep square root until you are able to take a square root. So just make sure you're not accidentally dropping those square roots before you take a square root. So this is what you're going to do when you see a perfect square factor. There's another thing I'm going to show you in a minute where you actually leave it or combine it as one radical so that you can simplify within it first and then take the square root. So you have to actually be looking for the patterns of when do I see something that's already going to break down and when do I have to actually put something together and then break it down. So let's try one more of these before we move on. Square root of 75 over 16t squared. So again, I see a perfect square factor here and here. Don't see a perfect square factor here, but I also see that that's going to simplify. So again, I'm going to split it into separate. Square root of 75, I'm going to simplify on its own. And then square root of 16t squared, I'm going to simplify on its own. So look for a perfect square factor of 75. And that's 25. So square root of 25 times the square root of 3 would get me back to the square root of 75. Over square root of 16 times square root of t squared. And now I'm just going to simplify each piece. So square root of 25 is 5, root 3, over the square root of 16 is 4, square root of t squared is t. And then I check to make sure 5 over 4 doesn't simplify. And it doesn't, so you're done. would be simplifying the radicals by dividing first. So that's where you would leave it all under one square root together, simplify the fraction, and then find the square root. For example, this is example 6. If I had something like the square root of 88 over 11. Notice here, no perfect square in either of these. There might be a perfect square factor, but these aren't perfect squares. And what I do realize is that 11 divides into 88 pretty easy. So I'm going to go ahead and just divide 11 into 88 instead of splitting it up, and get 11 goes into 88 8 times. So I have the square root of 8. Now the square root of 8 is really easy to break down, because I can break down the square root of 8 into the square root of 4 times the square root of 2. And I get 2 square root 2. Square root of 4 was 2, square root of 2. And I'm done. Okay, let's try another one. So we have the square root of 27a cubed over the 20 over 12a. So what I see here is I notice there's no perfect square, but I do notice that there's perfect square factors in 27 and in 12. I also notice there's a common factor between 27 and 12, so I could reduce this fraction before I try to simplify any further. And as we learned in chapter 7 with our exponents, I can also simplify this right here, the a cubed and the a. They're both underneath the square root. If these weren't both under the square root, I would not be able to simplify that. You can only simplify if they're both on the outside of it or if they're both on the inside. Otherwise, you can't start canceling things. So I'm going to go ahead and rewrite this so that we can see both of them. So I have 27a cubed over 12a. And I'm going to simplify. This a cancels and this a becomes a squared. And then I also have a common factor of 3 between 27 and 12. So 3 goes into 27 9 times, and 3 goes into 12 4 times. So now I have the square root of 9a squared over the square root of 4. This a is gone. Square root of 4 was left here. Square root of 9a squared was left at the top in the numerator. I split them up now because I noticed I had perfect square factors that I could start simplifying. Otherwise, I could have left it as a full square root and looked to see if anything else simplified further. So now I'm ready to simplify the numerator and the denominator individually. Square root of 9 is 3, square root of a squared is a, square root of 4 is 2, and that's my answer. So when you're solving these this way, what you want to do is simplify the fraction first, then take the square root and simplify. So this is the one that you're going to use when you don't see perfect square factors. Okay, so you use that when you don't see a perfect square. The last example is something that you need to learn for these. It's called rationalizing the denominator. And basically it's just a rule that mathematicians have. And this rule is that you're not allowed to have a final answer, a simplified answer, with a square root in your denominator. And so I'm going to show you what you do when you end up with a square root in your denominator. So this is called rationalizing the denominator. You're allowed to have square roots in your numerator, just not in your denominator once you have a final answer simplified. So we can't have a square root in our denominator. And I'm going to walk you through the example before I write down the rest of the notes on the left here. This is example 7. So let's just say we did all this work and we simplified something, and we end up with at the end an answer that looks like this: 2 over the square root of 5. So 2 doesn't break down any further, square root of 5 doesn't break down any further, but the problem is, in order to have a final answer here, simplified fully, I'm not allowed to have this square root in the denominator. So you have to go back to thinking about what we talked about earlier with those matching squares, or just what could I multiply this by to get a perfect square? And in this case, multiplying 5 by 5 gives us 25, and the square root of 25 is 5. So you get to follow the rule that you know about multiplying fractions by values of 1. If I was going to multiply this by a value of 1 and I wanted this to become a perfect square, then what I'm going to do is have my 2 over the square root of 5. And remember, if you're multiplying the numerator, you have to multiply the denominator by a value of 1. So if I'm going to multiply this by the square root of 5, I'm also going to multiply the numerator by the square root of 5. And if you think about it, that would cancel and become a 1. So that's why we're allowed to do that. But now what happens when we do that is we end up with 2 square root 5 at the top in our numerator. At the bottom we end up with the square root of 25, which actually becomes 5. So now we have no more radical in the denominator, and we're allowed to have it in the numerator. So you're just looking for what can I multiply numerator and denominator by that's going to give me a perfect square at the bottom. All right, let's try one more. Square root of 7 over the square root of 8n. Some of you might notice right now that square root of 8 has a perfect square factor of 4. If you wanted to, you could break that down now, but you know that this isn't going to break down perfectly, so you know you're still going to have a square root that you're going to have to get rid of at some point. So you might be better off just looking, is there something I can multiply 8 by that's going to give me a perfect square? And you probably figured out that's 2. 8 times 2 is 16, and square root of 16 is 4. What can I multiply n by to get a perfect square? I can multiply it by n, because then I'd have n squared. So if I was to multiply this by 2n, by the square root of 2n, I would have the square root of 16n squared, which is a perfect square factor. So that's what I'm going to go ahead and do. So I'm going to multiply this by the square root of 2n, and if I multiply the numerator, I have to multiply the denominator. So now in my numerator, I have the square root of 14n over 16n squared, square root of 16n squared. Now you have to always make sure, does the square root of 14 break down? Is there a perfect square? I know 7 and 2, but neither of those are perfect squares. You're always looking for perfect squares, because 7 and 2, you're not going to be able to break those down, so you're just going to end up multiplying them back together and being back at 14. So there's no perfect square that pulls out of the numerator. So square root of 14n comes over. And then the square root of 16 is 4, and the square root of n squared is n. And that's my solution simplified. No square root in the denominator. And these always get a little confusing, so we'll work on them tomorrow. Okay, so the rule for rationalizing the denominator is you're going to eliminate the square root by multiplying the fraction by a number or a term that makes the denominator a perfect square. Don't forget, it has to be the numerator and denominator when you multiply. So I kind of made that small, but your numerator and your denominator, you have to multiply both because it needs to be a value of 1. So if I'm going to multiply by the square root of 4 here, I have to multiply, or let's make it 14 so it's not a perfect square. Then I'm going to have to multiply by the square root of 14 there also. And the reason is because that's equal to 1. And then the other thing to be aware of here is those matching factors. Square root of 5 times square root of 5 is a 5. Square root of a times square root of a is an a. They'll always come out that way. So there's a chart in your book that kind of explains when you know you're in simplest radical form. This will kind of review everything that we just looked at. So you know you're in simplest radical form when the radicand has no perfect square factors other than 1. Obviously, you could spend all day long pulling out the factor of 1, and nothing's going to change, so you don't want to keep doing that. When the radicand has no fractions. Because you always want to look and break those down individually. The answer can be a fraction. It's just your radicand shouldn't have a fraction within it, because then you're back to this rule of having a radicand in the denominator. And then that leads to the third thing, which is the denominator has no radicals. And these kind of relate to the same thing. So tomorrow in class, we're going to be working on homework over this lesson. And you'll be able to ask me any questions that you have about the notes. You'll be able to try some of the problems and see if you get stuck anywhere, and we can work on it from there.